Hey everybody. So we're going to do in this video, this will be a pretty short one, just a quick review of what are called conics sections. And we're not going to dive very deeply into them. You've probably seen them before, but we're going to start with a geometric interpretation, and then we'll look at the equations of these particular kinds of curves, and that will lead us into our next idea. So we call these conic sections because one way to arrive at them is to start with a cone. So here is a cone in 3 dimensions, right? So it's a 3-dimensional or a 2-dimensional surface in 3-dimensional space. So you probably can imagine what this shape is. I hope it's clear from this. And we're going to take this cone and intersect it with a plane, right? So just like a flat, perfectly flat surface, like the XY plane. So here is a plane. So we're looking at it from the side right now, but if I move around, you see that it's actually like an infinite sheet of paper, right? And it's intersecting that cone. And I can change the way in which this intersects this cone, right? So just to be clear, this cone, imagine it going off infinitely in all directions and the plane going off infinitely. The computer just stops at a certain point rendering them. So don't let these edges fool you. They would both just keep going forever. So depending on how I intersect these, the shape of those intersections are different, right? So for instance, well, let's start with the one that I had when I turned it on. Here's this intersection where I'm at a slight angle. Let's look at that intersection. So if I turn this around and kind of look down the barrel of that cone, what we see is an ellipse, right? And if I slightly change how I'm intersecting, I get a different sized ellipse. There it looks pretty close to a circle. It's not quite a circle. And let's, if I go vertically, so now I'm perfectly vertical, this intersection here is, so again, the intersection, maybe I'm not clear about that I'm talking about, is where this dark red meets this teal, I guess, right? So just that line. And so this is a shape, it looks a bit like a parabola, which is another one of the shapes we'll get in a second, but this is something called a hyperbola, right? And again, depending on how I'm intersecting, the shape of that hyperbola can change. Now the intersection's on the other side, we don't see it anymore. Let me come back, there it is, right? And I can change exactly how that hyperbola is arranged. Oops, I want to keep that at 1. And let's see if we can get a parabola. Let's go this way. So here we should see a parabola. Wait, not quite. There we go. Right, so there's the parabola, the intersection there between this cone and this plane, right? So what we do with this idea, right? So let's do this. Imagine drawing this intersection. Oops, I didn't mean to zoom. How do I zoom out? Something like this. So I'm going to do something here that may or may not work well. We'll see how it goes. Let's trace this shape. So this intersection, right, there's my graph. Let's get rid of the cone for a second. Oops, I need to. So now I've just got this plane and I've got this curve of intersection on it. I could draw so pretend those are straight. I could draw a set of coordinate axes on these, and then I could come up with an equation for that parabola. And I could do the same thing for all of the shapes that we just saw. So that's how we move from these weird intersections to then something, right, we're familiar certainly with ellipses and parabolas, and we'll see hyperbolas as well. So we're going to take this intersection of these in 3-dimensional space to our flat plane in the way I just described here, right? If we look at that intersection and take the plane that's doing the intersection as our X, Y plane, we can now talk about these shapes in terms of the coordinate system that I'm imposing on that plane. So let's jump. Let me turn these annotations off. Let's jump to a two-dimensional graph. So, but first, let's write down what these equations look like, right? We looked at it geometrically, so we'll come back to this graph in just a second. But I've written down here on the left are three kinds of conic sections. And it can be determined, we can write down the form that each one has, meaning the equation that maps that curve of intersection onto that plane when we introduce a coordinate system. So the ellipse has an equation that looks like this. Or it can be put in this form, right? You don't always necessarily see it this way. So in this equation, x and y are the variables. H and k are the center of the ellipse. And the a and b are also constants. So h and k are constants, a and b are constants. H and k determines the center. A and b determine how, right, how stretched we are in either direction, right? So what we're looking at the graph right now is an ellipse where a and b are the same. That's a circle. It's not, they're stretched evenly, let's say. But if we change a and b, which we will in a minute, we can see that that circle will change. A hyperbola has nearly the same equation. In fact, it's so similar. Why don't I just copy? But there's one difference. This plus is now a minus. You can also put the minus on the x term and the plus on the y. I'm just going to write it in one version here. Okay, and so in a similar way, h and k are what can be thought of as the center of the hyperbola, and a squared and b squared, a and b determine certain things about the shape, right? Just like with the ellipse, how much they're stretched in certain directions. And then parabolas, we're used to seeing them, right, as quadratics. We're going to think about it a little bit differently in this. One way to write down a general, or the form of the parabola with a center at HK again. There's going to be two different ways depending on if it's going off to the left, up vertically or horizontally. So, oops, that should be a K. Right. So P is just, again, a constant that helps determine the shape of the parabola, how wide or narrow it is. H and K are the vertex of the parabola. And then whether the x term is squared or the y term is squared, right? If x is squared, that's the one we're used to seeing. It opens vertically up or down depending on the value of P. And then if it's the y term squared, it's a horizontal parabola, okay? So those are our three conic sections and their typical equations. So let's just take a look at them. We've got right now a circle. So what we're looking at is that equation. I've got it typed in here. Let's go full screen. And so if I change the values of these constants, right? For instance, if I change h and k, I can move it around. If I change a, for instance, that's the constant under the x term, I'm making it wider. It doesn't actually matter if it's negative or positive because it gets squared. If I change the b term, right, now I can make it narrower vertically or wider vertically. And if I make them the same again, we end up with a circle, right? So that's what h and k move the center around, a and b change the shape of it. Let's look at the hyperbola. So if I move h and k, right, you can kind of, the center is between, there's strict definitions. We're not going to get into the details, but if you look at what we might think of as the vertexes of each of these two shapes, in between them, in the center of the line segment connecting them there would be our center. So we can move it up and down. A and B change how narrow and wide it is, or how far apart they are. Right, so again, you get these shape dynamics coming from the A and B. And then let's do the parabola. So I've got two parabolas up right now. Maybe we'll just look at one first. Let's look at just the more traditional one. Here, H and K change the vertex, and P determines how wide or narrow it is, and also if it's facing up or down, positive up, negative down. We can do a similar thing in the other direction. P changes how wide or narrow it is, or whether it's facing left or right. Now, here's something you might not have noticed while we were doing all this. Every single one of these shapes I looked at let's see where it is. Oh, I know what I did. There's my parabola. That's too much. Let's just look at the ellipse for a second. When I changed all these values, it was always the case that this thing was, let's say, oriented with our axes. What I mean by that is if I connected, let's draw a line in here. If I look at the point furthest over here and the point furthest over here, and I connect that with a straight line, and if I do the same thing from top to bottom, if I could find the exact lowest and highest point, those lines would be parallel to the X and Y axes respectively, right? It's aligned with it. But we can imagine it's possible to have an ellipse at an angle, right? Same thing with the parabola. Everyone we looked at was kind of, if you drew a line down, it's we call axis of symmetry. That axis of symmetry was parallel to the y-axis or parallel to the x-axis, right? But we're not limited to just those. So let's turn this off. There's a more general form, for all of this. Every one of our conics can be written as ax squared plus by squared plus cxy plus dx plus ey plus f equals 0, where a, b, c, d, e, and f are constants. Okay. Oops, let's turn the annotating off. So let's look at this equation. Here is that equation where I've chosen a and b to be 1 and f to be -1, right? Which gives us x squared plus y squared minus 1 equals 0, or x squared plus y squared equals 1, which is the unit circle. But if I start changing these constants, right? For instance, I'm changing a and b, it turns it into ellipse, or if I change it enough, it becomes a hyperbola. If I change b, I can get different kinds of things happening. Let's see what goes. Oops. Right, so we get all kinds of different shapes happening. If I change D, I can move it off to one side. If I change E, I'm moving it up and down as well as changing the side. If I move F, I change my size. Again, A and B can turn this into different kinds of things. If I turn A to 0, we get a parabola. Or if I turn B to 0, I get a parabola. As long as A is not 0 at the same time, I get a parabola that we're used to facing up or facing down. However, so these are all the same. Everything I've just showed you now with this general form, given the values of A, B, C, D, E, and F that I'm choosing in my controls over here, we could reform it into one of these versions that I gave you just a minute ago, right? We can manipulate this equation to get there. However, there's one thing that those equations don't have, and that is C. I've kept C 0 this whole time. But if C is not 0, we start to get things at an angle. All right, now it's not so nice. Now I've got an ellipse turned to the side. Right? or depending on what I choose, right, I get an angled parabola or hyperbola. So there's all kinds of things that can happen if that C is not 0. And so the ones we're used to looking at, the conic sections we usually deal with are classic equations of a circle or an ellipse. We have C equal to 0. But when it's not 0, we get things that are turned on its side, which might seem like cheating. Why have we ignored this whole thing? Well, let's go back to remember what we did here. We were intersecting with these planes, right? Well, if I wanted to, so here, let's do this. Let's do what I did before. I'm going to draw the intersection again. All right, so I'm just going to look at the top half of this hyperbola. And then we got rid of the cone. We just thought about this plane. And then I drew in a set of axes, right? Well, one obvious thing to do would be to draw it like this, so that my hyperbola is aligned with that. Even though looking at this screen, it's a little bit to the side. I can always do that. I can always set my axes up to be aligned with making these things not be angled the way we were talking about, right? Now, it's not that I have to, right? I could draw my set of axes like this and call this the x-axis and this the y-axis, and now my hyperbola is going off at a weird angle, but it would make the equations more complicated, right? So where we're going to go next, that'll be it for this video, but where we're going to go next is we can always, if somebody chooses a coordinate system for us, maybe it comes from some situation where the coordinate system made sense, we can always rotate the coordinate system. We can choose a new one. So if my XY coordinate system is given this way, I can turn it into one so that my hyperbola is perfectly, is oriented around the X and Y axis. It's not at an angle like this. And so that's what we're going to get to next. How do we make sure we can choose these in the simplest form? Because that XY term can make things very complicated, but if we choose new coordinates, it can make things very simple. So that's what we'll talk about in the next one. Thanks, everybody. I'll see you next time.